Hey everybody!
Today we're going to be learning about
chemical equilibrium.
Woo!
So a lot of times when you have a chemical reaction, the chemical reaction will go in one direction, but then it can also go backwards in the opposite direction. For example, a lot of times when water, H2O, which is a liquid, turns into a gas, we call it water vapor, it forms H2O gas, okay? But as H2O gas cools off, that reaction can also start to go backwards. So you have basically the state of what's called equilibrium, where you can have some water in the liquid form and some water in the gas form, and they're kind of going back and forth, okay? This happens a lot of times in chemistry, and even in real life. It happens in your body when your body releases the oxygen in your hemoglobin. That's more of a biology reference. And even carbon, if you think about the carbon cycle, in the carbon cycle, there's also a lot of chemical equilibrium. And just in chemistry in general, there are a lot of reactions that as the reaction starts to go forward, it also starts to go backwards as well. Okay? Because the products will also start reacting with themselves to reform the reactants. Now, when a reaction starts, typically you're just starting with the reactants, and so the reaction only goes to the right. Okay, but as you start to form more and more products, the products start to reform the reactants. Okay, and basically what happens is, in terms of, for example, let's say reactants, or let's say reactants and products. So the reactants, the amount of the reactants goes down, goes down, goes down, goes down, goes down, goes down, goes down like that. And then the amount of the products, this is a P down here, the amount of the products goes up, goes up, goes up, goes up, goes up. But see how you get to a point where basically it gets flat, maybe right around there. It gets flat, okay? And at that point, it looks like nothing is changing, but all that means is the rate, which is the speed, the rate of the forward reaction is equal to the rate of the backwards reaction. Okay, that's at this point right here, that's the point where you have reached equilibrium. So, for a reaction to reach equilibrium, some time has to pass. You have to let some of those reactants turn into products, and then those products have to start producing reactants again. Okay, and of course, as the reaction proceeds, as we just saw, the concentration of the reactants is going to go down because you're using those reactants up. And the rate of that forward reaction will start to decrease. The speed that the water turns into a gas is going to start to go down. And of course, the opposite is also true. As the product starts to increase, the concentration goes up, and the rate of the backwards reaction will start to increase. So again, that point where the speed of both reactions is the same means that that's when we have reached equilibrium. Okay, reaching equilibrium does not mean that you have the same amount on both sides. Okay, we'll see that in a little bit later as well. Okay, it just means that the rate of the forward reaction and the rate of the reverse reaction are equal to each other. And you might have more product, you might have more reactant. It doesn't matter. All that matters is when you're at equilibrium, the rate of the forward and reverse reactions are the same. So here we can see two different examples of equilibrium. One of the ways that really identifies an equilibrium reaction is that double arrow. Notice with a double arrow, you've got a reaction going forward and you've also got a reaction going backwards. So as this reaction here starts, the SO2-Cl2 is going to break apart into SO2 and Cl2. But as that SO2 and Cl2 start to form, those two start to react with each other to reform some SO2-Cl2. And then the SO2-Cl2 will break apart again, and what happens is that reaction just keeps going back and forth at the same rate once you've reached equilibrium. Okay, many times there's color changes involved. For example, this one here might be orange, and this one here might be blue. So what you'll find is at the beginning, the solution is very, very orange, but as the reaction proceeds, it'll start to turn more of an orangish-bluish color until it reaches equilibrium, and then it's just kind of a mixture of orange and blue together. Now, one of the things that we use with equilibrium is what is called the equilibrium constant. Now, this is kind of a misleading word, constant, because like when we learned about the gas constant is 0.082, and it is a constant. When we learned about the speed of light, it's 3.00 times 10 to the 8th meters per second. It's constant. It doesn't change. Even Planck's constant, the 6.63 times 10 to the negative 34th joule seconds, is a constant. It doesn't ever change. Okay? The equilibrium constant is not a fixed number. Okay? What it does, though, is it tells you about your equilibrium mixture. So first of all, let's talk a little bit about how do you figure out what the equilibrium constant is. So let's say we have a fake equation right here, where the capital A here is and the B, and the capital C, the capital D here. Those are the compounds. That's like H2O, NaCl, NaOH, whatever. Whereas the lowercase ones, the lowercase a, the lowercase b, those are the coefficients. Okay, those are the numbers. That's the 3 HCl plus 2 NaOHs. So that would be the 3. This would be, the capital A would be the HCl. Okay, so the way that you write an equilibrium constant expression is, notice right here. This is really, really important here. Notice that you take, first of all, you've got these square brackets. Okay, what do those square brackets mean? The square brackets represent the concentration measured in molarity. So let me go through this equation that we've got here. So KEQ, the equilibrium constant, is equal to, and notice how I say this, the concentration of substance C raised to the power of its coefficient. Notice this is a small c, a lowercase c right there. Okay, and C is a product. So notice the products are on the top, always, and the reactants are on the bottom, always. So it's the concentration of C raised to the power of its coefficient times the concentration of D raised to the power of its coefficient, and those are the products, over the concentration of the reactants. So the concentration of A raised to the power of its coefficient times B raised to the power of its coefficient. Okay, so it's written with the concentration of the products over the concentration of the reactants raised to the power of their coefficients. And here's one thing that's fantastic, is there's no units. There's no molarities, there's no seconds, there's nothing. The equilibrium constant is nothing more than just a number. Okay, let's look at a couple of examples here. Okay, number 1. It says the Haber process is a process by which hydrogen and nitrogen are converted into ammonia by the following equation. You've got 1 N2 reacting with 3 H2s to make 2 NH3s. And then it says write the equilibrium constant expression for this reaction. So we're going to write KEQ is equal to, remember, it's the concentration of the products over the concentration of the reactants. So it's the concentration of NH3. Do we have to put those square brackets? Yes, you do. Okay, and that's going to be squared over the concentration of N2 times the concentration of H2. And again, because that 3 there, just like that 2 that's here, I had to square NH3. With a 3 there, I have to cube the value for H2. Okay, and then example 2, it says dinitrogen tetroxide and nitrogen dioxide exist in a state of equilibrium, expressed by the following reaction. What is the equilibrium constant for this reaction? Okay, so KEQ is going to equal the concentration of the products. The only product is NO2, and there's 2 of them. So that's squared over the concentration of N2O4. Okay, and that's it. That's all you've got to do is products on top, reactants on the bottom. Make sure you set it equal to KEQ though. Don't just put this part. You've got to put that part is equal to the equilibrium constant. Okay, one more thing. Okay, KEQ is kind of like the generic way of writing this. Okay, when you're writing an equilibrium constant expression, a lot of times, like here you saw gases, here you see also just straight gases, okay? But a lot of times with equilibrium constants, you have in the same equation, you're going to have solids and liquids and aqueous solutions, right? I mean, you might have like NaOH. Oops, I don't know why I did that. Okay, aqueous and HNO2 aqueous. And that's going to create an equilibrium system with NaNO2 aqueous plus H2O liquid. Okay, and sometimes there's liquids and sometimes there's even solids in these. You might have like AgCl solid in equilibrium with Ag plus aqueous and Cl minus aqueous. Okay, and so what happens? What do you mean? What's the concentration of water in water? What's the concentration of a solid? What's the concentration of sand in some water? Okay, there isn't one. Okay, so first of all, solids and liquids are not included in the equilibrium constant expression. They don't have a concentration. So what do? You simply leave them out. Okay, so for example, here on this one, we would write KEQ is equal to the products, so the concentration of NaNO2 over the concentration of NaOH times the concentration of HNO2. Okay, and notice that I just completely left the water out. Okay, on this one up here, again, AgCl is a solid, so we would write KEQ is equal to the concentration of Ag plus times the concentration of Cl minus, and that's it. That's our product. That's what goes on the top. The reactant is a solid, so we leave it out. So solids and liquids you do not include in the equilibrium constant expression. Okay, so I'm gonna go ahead and stop there for now. So we're gonna continue our next video right here.